Have you ever truly considered an impossible problem? Not a hard problem, like building a skyscraper, but an impossible one, like simulating the first second of the Big Bang, or accurately predicting the path of a hurricane, atom by atom, or designing a new drug by watching how a virus protein folds itself into existence. If you gave your high-end gaming PC that last task, it wouldn't just be slow. It would take about 500 million years to get an answer. Yet at the Oak Ridge National Laboratory in Tennessee, a machine called Frontier can run that same calculation in about 2 days. How? What is the secret that makes this machine not just thousands, but millions of times more powerful than the supercomputer in your pocket? The answer is fascinating, because it's not just a bigger, faster version of your PC. It's a completely different philosophy, a different species of computation. Today, we go inside a supercomputer. We will peel back the metal, explore the nervous system, and reveal the fundamental idea that makes the impossible possible.
First, we have to break the biggest misconception. Most people think a supercomputer is just a really big PC. Maybe it has a 500-core processor instead of an 8-core one. This is fundamentally wrong. And to understand why, let's use an analogy: the banquet kitchen. Think of your home computer or your phone as one brilliant master chef. This chef is a genius. He can chop, sauté, bake, and plate with incredible speed. This is serial processing. He does one task, finishes it, and moves to the next. One thought, one action, one after another at blinding speed. Now, if you ask this one master chef to cook a 10,000-person banquet, he will fail. It doesn't matter how fast he is one person. He is a serial thinker. He will still be cooking appetizers when the 10,000th guest dies of old age. You can't solve this problem by just making the chef faster. Giving him a slightly sharper knife, going from a 4 GHz processor to a 5 GHz one, doesn't change the outcome. A supercomputer doesn't try. It rethinks the entire problem. A supercomputer is parallel processing. It is a kitchen with 10,000 chefs. We call these cores. But here's the key: they don't all know the full recipe. Instead, a head chef, the software, shouts, "Everyone, peel 1 potato, go!" And 10,000 chefs peel 1 potato at the exact same time. The task is done. Everyone, chop 1 onion, go! This is the secret. A supercomputer is not one thing. It is a massive, coordinated cluster of thousands of simple things, all working at the exact same moment on a tiny piece of the same giant puzzle. Your PC is a genius soloist. A supercomputer is a 10,000-piece orchestra playing one perfect, deafening note all at once.
So what does this 10,000-piece orchestra actually look like? When you see a picture of a supercomputer, you see rows and rows of identical black cabinets. They look like refrigerators in a data center. But let's pull one of those cabinets out. Inside, you won't find one giant motherboard. You'll find dozens of thin, hot-swappable servers stacked like books on a shelf. We call each one of these servers a node. Think of a node as one complete computer, with its own processors, its own memory, and its own network connection. The Frontier supercomputer has 9,408 of these nodes. But the real magic is inside each node. This is where we find the chefs. And this is where the type of chef becomes critical.
For decades, the chefs in our kitchen were CPUs, central processing units. A CPU is like that master chef. It's a commander. It's incredibly smart, versatile, and fast. It's designed to handle complex branching logic. If this happens, do that. Unless this happens, then do this. It's a brilliant serial thinker, perfect for running your operating system, your web browser, and your spreadsheet. But it's too smart for our 10,000 potato problem. A CPU has a few very powerful cores, but those cores spend most of their time managing tasks, predicting what's next, and handling complex instructions. It's overkill. Then the world of video games gave high-performance computing an accidental gift, the GPU, or Graphics Processing Unit. A GPU is not a master chef. It's an army of soldiers. A GPU is, by design, a parallel processing beast. It was built to do one simple, repetitive, dumb task. Take this 3D model and calculate the color for every single pixel on the screen. That's millions of simple math problems, pixels, that can all be solved at the same time. A single high-end GPU, like the ones in the new Aurora supercomputer at Argonne National Laboratory, doesn't have 8 or 16 smart cores. It has thousands of simple, dumb cores. They are dumb in the best way possible. They don't do complex logic. They just do math, fast, all at once. Scientists looked at this and had a revelation. Simulating a hurricane is just like rendering a video game. You divide the atmosphere into a million little cubes, and you run the same simple physics equations on every single cube at the same time. Folding a protein is the same. You calculate the simple electromagnetic forces between every single pair of atoms all at once. This is why today's top supercomputers, Frontier, Aurora, and the upcoming El Capitan, are what we call GPU accelerated. Each node in Frontier has one smart CPU, commander, to manage tasks, but it's paired with 4 massive AMD GPU soldier units. With over 9,000 nodes, Frontier has a total of 9,408 CPUs, but it has over 37,000 GPUs. That's not 10,000 chefs. It's closer to 11 million cores, all humming in unison. But having 11 million chefs is useless if they can't talk to each other.
This, right here, is the most secret and arguably most important part of a supercomputer. It's not the processors, it's the network. Let's go back to our kitchen. If Chef 5200 needs to know the temperature of Chef 2001 sauce right now, he can't send a text message. He can't wait. An eighth of a second delay, 125 millisecond latency, would be an eternity. The entire banquet would be ruined. Your home computer network uses Ethernet. It's great. But in the world of supercomputers, it's a horse and buggy. These machines use something far more exotic. The current standard is called InfiniBand. InfiniBand is not a network, it is a fabric. It's a dedicated nervous system designed for one purpose: moving massive amounts of data with ultra-low latency. We're talking millions of a second. It has a feature that sounds like science fiction, RDMA, or Remote Direct Memory Access. In a normal network, if Chef 5200 needs that temperature data, he has to ask his CPU commander. The commander has to stop what it's doing, package the request, send it to Chef 2001's commander, who then has to stop, fetch the data from his memory, package it, and send it back. It's a bureaucratic nightmare. With RDMA on InfiniBand, Chef 5200's processor can bypass both commanders entirely. It is given secure permission to directly reach into the memory of Chef 2001's computer and grab the data it needs instantly. It's the difference between sending a formal letter
and being telepathic. This fabric is the connective tissue that turns 9,000 individual computers from a crowd into a single, unified organism.
Of course, this organism has an appetite, an insatiable one. A supercomputer storage system has to feed data to those 11 million cores simultaneously. You can't use a normal hard drive. They use parallel file systems. Imagine a single giant file, like a 10 terabyte climate model, that is shredded into a million pieces. Each piece is stored on a different physical hard drive. When the computer needs the file, it reads from all 1 million drives at the same time, pulling the data in a massive parallel wave. Frontier's Orion storage system can deliver data at 10 terabytes per second. That is the equivalent of streaming 2,000 uncompressed 4K movies every single second. And all of this generates heat. A lot of heat. Frontier consumes 21 megawatts of power. That's enough to power a small city of 20,000 homes. To stop it from melting, it doesn't use fans. It's liquid-cooled. 6,000 gallons of water, pumped at 350 gallons per minute, circulate through the cabinets, pulling the heat directly off the processors. This hot water, now at 90 degrees Fahrenheit, 32 C, is then used to heat the adjacent office buildings, saving the lab money on its heating bill. It is a breathtakingly complex and yet surprisingly efficient ecosystem.
And look, we're going deep on this because understanding this technology is understanding the future. If you love these deep dives into complex tech, do me a favor and hit that subscribe button. We release videos like this every week, and it's the best way to support the channel. Okay. So we have the hardware, we have the 10,000 chef kitchen, we have the telepathic nervous system. One last piece, how do you write the recipe? You can't just install Windows on this thing. You can't open a program and click Go. You have to write software in a completely new way. You have to think in parallel. Programmers must manually break their giant problem down into tiny pieces. Let's go back to that hurricane simulation. A programmer doesn't write one program. They write a program that will be run by every single core at the same time. They divide the world map into a 1,000,000 square grid. Each core is assigned 1 square of the grid. The core's job is simple. Look at the current temperature and wind speed in my square. Talk to my 4 neighbors, the cores handling the squares north, south, east, and west of me, and get their temperature and wind speed. Run a physics equation based on these 5 values. Calculate the new temperature and wind speed for my square, 1 second into the future. Wait for all 1 million cores to finish, and repeat. This talking between neighbors is the key. The language they use is a standard called MPI, or Message Passing Interface. MPI is a set of simple commands, like a programmer's toolkit, that have existed for 30 years. It's the recipe book for our chefs. There's a command called MPI bcast, broadcast. The head chef shouts the same instruction to everyone. There's MPI scatter. The head chef scatters a big problem, giving 1 small piece to each chef. And there's MPI gather. At the end, the head chef gathers the small finished piece from every chef to assemble the final dish. A supercomputer program is a beautiful, terrifyingly complex dance choreographed with MPI. It's millions of processes, all starting, stopping, sharing, and waiting in perfect microsecond-level synchronization.
This brings us back to our original question. Why? Why build a $600 million 21 megawatt monster?
because it allows us to do something no other tool in human history can: high-fidelity simulation. We can now build digital twins of reality. Instead of just observing a black hole, physicists at Caltech can use a supercomputer to create a digital black hole. They can smash it into another one and watch the gravity waves ripple out in slow motion, comparing the simulation to what our space telescopes actually see. Instead of just testing a new jet engine, engineers can simulate the turbulence of every air molecule flowing over the turbine blade. They can test 10,000 designs in a week without ever building a single physical prototype. They are used for medical research. The Summit supercomputer, Frontier's predecessor, screened 8,000 different drug compounds to find ones that could stick to the COVID-19 spike protein, identifying 77 promising candidates in just 2 days. And now, they are the engines of the AI revolution. Training a massive large language model like GPT-4 is a perfect parallel problem. It's billions of data points being processed through a massive mathematical matrix, a neural network. The Aurora supercomputer, now online, is one of the first exascale machines, capable of over a quintillion calculations per second. And its primary mission? Not just physics. It is a dedicated AI supercomputer, built to train the next generation of massive LLMs for science.
A supercomputer, in the end, is not a fast computer. It is a coordinated one. It's not a single brilliant mind. It's a colossal colony mind. It's an architecture of massive parallelism, the kitchen, built from hardware designed for it, GPUs, connected by a telepathic nervous system, InfiniBand, and all of it brought to life by a language of perfect synchronization, MPI. These machines, Frontier, Aurora, El Capitan, are the first of the exascale era. They are our new cathedrals. They are the telescopes we point not at the stars, but at the very fabric of reality itself. They are the tools we build to solve the problems we thought were impossible, to simulate the universe, to cure disease, to understand intelligence itself. And for the first time, we are getting answers back. But what do you think is the most incredible part of these machines? Is it the raw GPU power, the telepathic InfiniBand network, or the fact we're using them to build AI? Let me know your thoughts in the comment section below.